Hello everyone, my name is Daniel Arango and I'm going to be doing my project on polyurethane and its use in control release fertilizer. So first of all, a brief introduction of polyurethane. This molecule is a polymer. It can be petroleum-based or bio-based. This means that for petroleum-based, that the chemical was developed using petrochemicals as a feedstock, so like petroleum and natural gas. Bio-based, the reactants are collected from plant oils or biomass. The benefits of using bio-based polyurethane over petroleum-based is that it does completely biodegrade and leaves no microplastics behind in the environment. It is, however, slightly weaker than the petroleum-based version. Polyurethane is a widely used molecule. It can be found in foam, insulation, sealants, adhesives, coatings, finishes, and different kinds of equipment, such as hoses or gears. So the properties of polyurethane, this molecule tends to be characterized or categorized, I'm sorry, to three different types. So it can be done through structure, its thermal response, or its source material. We just covered the source material when we spoke about bio-based or petroleum-based versions of polyurethane. With regards to structure, this molecule can be linear or hyperbranched. Linear, also known as LPUs, are long and have straight chains of repeating units. This version is characterized by its high resilience, durability, and its resistance to wear and tear. Typically, films and foams are made out of the linear version, and you can think of a sponge, for example. Hyperbranched, also known as HPUs, have large numbers of complex branches. They have a higher surface area, lower viscosity, and are more soluble. This makes them, of course, better as coatings or adhesives. With regards to its thermal response, thermoplastic, also known as TPUs, retain its original properties even after being melted and recasted. It resists abrasion, oil, and UV radiation, as well as shock and vibration due to its elastic properties. You can typically find this type of polyurethane in hosing, films as well, or protective covers. Thermosetting, so TSUs, are rigid, high strength, and very tough, making the material retain its shape and properties. It can't be reshaped when melted, unlike the TPUs. They resist abrasion, are good electric insulators, and resist UV light and chemicals well. This is what makes them really great for electrical equipment, gears, bearing, nozzles, things of that sort. So taking a step back from polyurethane for a moment, let's consider the NASA Veggie Project. This is NASA's program where they're growing veggies on the ISS to see how plants grow in microgravity situations, as well as seeing how to grow plants off of Earth, right? So eventually we can do that on Mars and potentially continue doing it on the ISS so our astronauts can have fresh food. Um, NASA partnered with Florican, which is a Florida-based fertilizer company. And they're the ones, or well, the founder of Florican was the one that created the patent for polyurethane coated fertilizer pellets, control release fertilizer pellets. And these are the ones that are currently being used by the Veggie Space program. So what are controlled release fertilizers, also known as CRFs? Essentially, a CRF is when a fertilizer core or similarly, nutrients required by plants are encapsulated in a semi-permeable coating or membrane. Water or another chemical will diffuse through this coating and dissolve the nutrients inside. Once these nutrients are dissolved, they'll steadily permeate out of the pellet and are then consumed by the roots of the plant. One benefit to using this technology is that it makes sure that the plant gets preferred nutrients during the specific stage of growth that is most convenient. So, for example, plants require different concentrations of nutrients when it's just coming out of its seed and forming roots and its stems, when it starts to create a bunch of leaves, when it begins to flower, when begins to fruit. All these stages in its life cycle, the plant prefers different concentrations, and those can be tailored by choosing a specific coating or changing the conditions of the soil so that the coating will adjust accordingly. Here's a simple 3D model of a CRF pellet. As you can see on the very left, the blue you can consider your polyurethane coating that is completely covering the fertilizer core. In the middle, we see it cut through the middle, where inside the essential molecules or nutrients for plants, which are nitrogen, potassium, and phosphorus, are located. The final model on the far right shows the nutrients diffusing steadily through the barrier. This, of course, varies depending on the conditions in the soil and the type of coating used. The production of a simple CRF pellet coated with polyurethane can be summarized in 3 steps. First step, fertilizer is sent into a rotary blade while it is heated to remove any moisture. The second part includes polyol being added to the fertilizer mix, and then isocyanate being added separately. Third, this process is repeated until the desired coating by weight is achieved. If you look at the background of the slide, you can see the simple formula, that is the isocyanate reacting with the polyol, which is what creates your polyurethane. This slide goes over a few of the benefits to using polyurethane as your preferred coating for CRF pellets. First benefit being that bio-based polyurethane is sustainable because it completely biodegrades in the environment. This means that no leftover harmful chemicals or microplastics are left in the environment. Another benefit is that CRF pellets using polyurethane can last up to 360 days, meaning that it's approximately an entire year's worth of fertilization just from one dose. This means that plants using this type of fertilizer require a lot less manpower because it doesn't need to be as frequently fertilized. Another benefit to using polyurethane is that the diffusion rates can be modified or tailored towards specific pH, humidity, temperature, or other soil conditions, thanks to polyurethane's variety of forms, as we discussed previously with its linear and hypobranch forms. And lastly, here are my references. I hope you all enjoyed this presentation and learned something about either CRFs, polyurethane, or at least you found the NASA Veggie Space Program. That'd be cool. Have a great rest of your day. Bye bye.